Anyway, through a telescope, uh, both Uranus and Neptune uh, kind of look like twins. Um, I mean, we have seem to have a lot of planets that people call call us twins, but I mean, aside from the fact that one is uh, considerably further away than the other, they both look just as nebulous as each other. One of them is slightly greener than the other one. Um, and in fact, according to a children's book, these were called the Green Giants. I suppose that was in 1959. And I suppose somebody sued them when they called it the Green Giants. By the way, there's the book. And that's actually the revised edition of that astronomy book. The first edition was 1954. So, and that's interesting. But they called it the Green Giants. But I have trouble believing that Uranus and Neptune were considered twins. I mean, being twins doesn't mean you have to be identical. Um, here's Mark and Scott Kelly. It's pretty easy to figure out which one's which. Mark is the one with the mustache. And then, of course, we have another set of twins, and these are quite famous as well. Actually, in real life, they are actors from, I believe they are from Ontario. Um, and this, I'm not, they look almost identical, but they are somewhat different. Uh, the Earth and Venus have been called twins. And really, the only thing you can even say one is like the other is the fact that Venus is just a tiny little bit smaller than the Earth. If you take away the clouds, then you have something else, and these are definitely not twins. Um, I suppose there's another way you can look at twins, but I'm not quite sure you want to get into that. 1958, 1959, Rand McNally came up with a solar system. And it's interesting because they do show uh, Uranus and Neptune, uh, in the colors that you see them as green and blue. Uh, but I wouldn't put a whole lot of stock in this. For one thing, the red spot on Jupiter is absolutely huge. The other thing is that little thing up there called Sirius, which is a dwarf planet, actually looks more like this. So I'm not quite sure where they got that particular picture from. A little bit later on in the early 1960s, Ronald McDonald came into view, but at least they held Uranus and Neptune uh, as twins or close to being twins. So once again, we have our solar system. We have the inner planets and the outer planets. We have the terrestrial planets, Earth-like, although I would be very hard pressed to call Mercury Earth-like. But then you have the gas giants, the outer planets, and yeah, they are kind of gassy, you'd say. Um, I don't think I'd put much faith in comparing Saturn and Jupiter as being the right size, but and certainly Uranus and Neptune are way, way too big. But if you look at them as far as just individual planets are concerned, um, here are the inner planets, the terrestrial planets, going from left to right. We have Mercury, Venus, Earth and Mars. These are rocky and relatively small. And then we have the giant gas planets. Again, left to right, we have Jupiter, Saturn, Uranus, and Neptune. And these are, at least as far as size is concerned, pretty much to scale. So tonight we're going to be taking a brief look at the ice giants, Uranus and Neptune. And to start off with, both Uranus and Neptune were discovered with telescopes. Although Uranus, you don't need a telescope to be able to see it, although it would help a great deal. And the first one to actually find Uranus, and again, he used a telescope, was William Herschel in 1781. You have the Earth and Uranus here, and they are to scale, so to give an idea of how much bigger Uranus is than the Earth. Anyway, William Herschel was a music teacher and a composer, and he, like any other mathematician, and since he was a music teacher, he was heavily into math. He took the opportunity when he discovered Uranus to figure out its orbit. And what he found was quite interesting. The fact of the matter is the orbit wasn't exactly what was predicted by Newton's laws. It was a little bit different. So at the time that he discovered Uranus, he was actually looking for comets. And he was pretty frustrated by this particular object because it wasn't a comet. But I guess he did at least make up for it by discovering a planet. He decided that he wanted to name this planet George, and which he did. But it didn't stand, so they named it Uranus after a Greek god. So in the process of discovering Uranus and trying to figure out its orbit, he discovered that the orbit wasn't quite right. So based upon that, there had to be something that was pulling on it. And so the search for another planet was started. And the planet Neptune was discovered in 1846, about 70 years later. And it was actually discovered two different ways. Based upon how much it was displacing Uranus, Neptune's orbit was figured out. And okay, not sure who Stephen W. is, but we'll get him in there. It was discovered mathematically by two scientists, one of them named Leverrier, and then a astronomer named Johann Galle was looking for it, and he took what the mathematicians did, and he looked for it where it might have been. So mathematically, Newton's laws of gravitation were confirmed, and when they set out to try to find the particular planets, the mathematicians predicted it over here, but the observational astronomer found it over here. So this was actually the first planet ever to be at least discovered, not only by mathematics, but also by observation. What throws a wrench into this whole process was the fact that Galileo discovered this particular object more than 200 years before that. He was watching an occultation of this particular star by Jupiter, and his notes are quite complete. And he discovered that this particular object, he thought it was a star. Looking at his notes and looking at his observations, 300, 400 years later, it was discovered that he had actually saw the occultation of Neptune by Jupiter. So, but we really can't give him credit for that simply because, well, he didn't call it a planet. Anyway, but while watching all of these things, we find out that all these planets do rotate on their axis, not all the same. Jupiter rotates in a little bit less than 10 hours. Saturn rotates in a little bit more than 10 hours. It takes Venus, the better part of 2/3 of an Earth year to make one rotation. And then Uranus actually rotates sideways. So there's certainly a lot going on as far as that's concerned. What would be interesting is if you lived on Uranus, or Uranus, I should say, sorry, it's a habit. Yes, I see you shaking your finger. If you lived on Uranus, you would find that the movement of the sun across the sky, other than the fact that it would be quite small, is quite weird. We would be facing, there would be times when we would be facing the sun, and the sun would be rotating around the zenith or high point in the sky. And then at other times, for about a number of years, it would be on the other side of the. Let's try that. It would be on the other side of the planet, and it would be in perpetual darkness. So it's what you might actually have as you're watching the sun move across the sky. This is not an exact representation, but it does give you an idea on how weird the sun would move across the sky. It would actually spiral up to a point. It would actually spiral up to a point and then go back down. And as you can see, the shadow would slowly move across the sky as the sky goes into darkness for another 42 years. So the gone. So now we'll have 42 years of nighttime, 42 years of daytime, and it certainly isn't a very conducive planet to do any kind of work. Now, in the early 60s, a technician, actually a mathematician, who worked for a jet propulsion laboratory, actually found that at some point in the future, the planets would be lined up so that you would be able to actually skip from one planet to another using the gravitational pull of each of those planets. And you wouldn't have to waste a whole lot of fuel in order to get out to, well, let's say if you wanted to get out to Neptune. Name of that mathematician was Gary Flandreau. And he actually came up with a name for that. He called it the Grand Tour. Now, In the early 1960s, when he came up with this plan, using gravitational assist was a brand new, was pretty brand new. Actually, the only thing that it was used for was in 1959 by the Russians, who used it, used the Earth's gravity to take Luna 3 and whip it around the Earth so it can go all the way out to the moon, where it actually went around the back of the moon, taking pictures of the backside of the moon. Well, that worked out pretty well, and he started figuring out what would the path of those particular spacecraft be like. So he figured out that if they were launched in 1977, they can be out to Neptune in about 12 years. Well, this was absolutely amazing. The fact that they can actually take a spacecraft and move it that far in 12 years. What was really amazing was trying to build a spacecraft that would be that reliable to be able to make it 12 years. So they were basically taking their knowledge of gravitational slingshots and started figuring out what would happen if they moved past a space after a planet, and they found that the spacecraft could move a great deal faster. However, the planet does move a little bit slower because the spacecraft takes a little bit of energy out of the orbit of that planet. Of course, when you start comparing the masses between the two objects, there's absolutely no problem at all, simply because the planet would have so much more mass that it wouldn't make any difference. The problem comes in trying to figure out the angle where you want where you want to move your spacecraft. Since gravity is, well, 3 or 4 dimensional, you would have to figure out that angle very, very precisely, because a mistake would send that object off in a whole different place. So, to give an idea of what was going on, we have our gravitational well, and a spacecraft would simply be changed depending upon how deep in the well that spacecraft went. The deeper it goes, the more energy it pulls from the planet, and the faster it goes. So if it goes a little bit deeper, you can actually get more of a ride out of it. And then if you go really deep and get your angles precisely, what you find is the fact that you gain energy and the object will go off, hopefully, in the direction you want it to. So that's what they decided to do. That's what they were looking for. They figured out that as the probe would approach the planet, its velocity would increase tremendously. And then after it left the planet, it would lose velocity, but would always pick up just a little bit. And as you can see, this is Voyager 2. When it passed Jupiter, its velocity was pretty close to 30,000 kilometers per second. And then it would lose its velocity as it went further out, but it always remained faster than the solar system escape velocity. So they knew whatever it did, it was going to leave the solar system. So they decided they were going to build the spacecraft. It had to be absolutely reliable, and it couldn't use batteries since simply because at 12 years, the Energizer Bunny would be long dead. So they decided that they had to use something else. So looking at it, you can see that there's something called a radioisotope thermoelectric generator, or RTG. What in the world is an RTG? Well, all of you, whoops, if we were to look at the sun from each of the planets, you can see that here on the Earth, we have a nice bright sun. From Saturn, the amount of sunlight that we would receive would be less than 1/100th that of the Earth. So we needed something other than solar cells to be able to generate that electricity. The fact that we have so many on the International Space Station is basically a testament to the fact that we are an awful lot closer to the sun than Uranus or Neptune are. And so we had to come up with something, and that was the RTG. Now, all of you are familiar with the pilot light on your, um, let's say if you have a gas heater or something that requires a flame or heat. That thermocouple actually has two pieces of metal in it. It's called a bimetallic metallic strip. And that, that metal will actually, through heat, will generate a little bit of electricity. So if we can generate some heat, we could actually make electricity. Now, how do you do that in a spacecraft? You do that with radioactive isotopes. In this particular case, we're using plutonium-238. It has the lowest shielding requirements and the longest half-life. The half-life of plutonium-238 is 87 years. That means in 87 years, it's lost half of its radioactivity. So they were going to build some type of generator, heat generator, using plutonium-238. And this was done as early as the first, actually the first weather satellites used uh, plutonium-238. And then later on, we had this particular generator appear on various spacecraft like Pioneer, the Vikings, both 1 and 2, Galileo, which went to Jupiter, New Horizons, which went out to Pluto. And so we had this thing to be able to generate electricity all the way out, actually beyond, well beyond our immediate solar system. And right now there are several of these on Mars generating electricity. So now we had everything we needed to be able to build a spacecraft to get out beyond Jupiter and Saturn, all the way out to Uranus and Neptune. But we had to test out the theory. So Voyager 1 was the first one to do this. And Voyager 1 took off in 1978, actually September of 1978, and it took off for Jupiter and Saturn. And the results of that probe were absolutely amazing. This is where we discovered the bands, the moving bands of Jupiter, and how the bands went around the red spot. We also discovered, taking a close look at the 4 Galilean moons of Jupiter. We found a volcano, an active volcano on the moon Io. So this was a major, major discovery. We also discovered how the red spot, how the storm on that red spot generates so much heat that some scientists feel it generates most of the heat the planet radiates. It discovered rings around Jupiter, which were extremely hard to see simply because they're so nebulous. And of course, it took a very good picture of the magnetic fields that Jupiter generates. It went on to Saturn, where it took a real good picture of the rings of Saturn. It discovered that Saturn had more than 6 rings. It actually had a whole variety of rings. It discovered that those rings were not consistent. It also discovered the hexagonal cloud features that were above the poles. It also discovered the shepherding uh, uh, moons of Saturn that keep the rings in check. They decided, rather than going on to uh, Pluto, they decided they were going to go on to Titan and discover, because with looking at Titan through telescopes, they discovered that Titan had some type of an atmosphere. So they changed the trajectory of Voyager 1 so it no longer had the trajectory to go out to Pluto. Now it was going to go past Titan. And they discovered Titan's hazy atmosphere. They discovered that the uh, gases on Titan were methane, and from Titan, the spacecraft went on to take a trip beyond our immediate solar system. Actually, before Voyager 1 was launched, Voyager 2 was actually launched ahead of it. One of the things you have to consider is the fact that all of the data is saved. And years later, we have better ways of accessing that data to be able to get better pictures of the planets and what we're looking at. This is true with Hyperion, a moon orbiting Saturn, using data that was stored from Voyager 1. They were able to uh, basically re-image that particular moon, and we got a lot more information out of it. All of the information by all of the probes are saved so that scientists can go back and actually access this data and learn some more about it. Next one, actually what was blasted into space before Voyager 1 was Voyager 2. And as you can see, it went past Jupiter, Saturn, and then it made the long trek out to Uranus and finally Neptune. So the big question is, what is a Uranus? It's the seventh planet from the sun, fourth largest planetary mass. Uh, it was discovered by William Herschel. Neptune, the furthest planet from the sun. Of course, some of us remember Pluto. We remember when Pluto was a planet, but of course, Pluto's orbit actually takes it inside of Neptune's orbit. So for about 20 years, uh, Neptune is actually the furthest planet. So if we take a closer look at each of these, what we find is that the interior of Neptune and Uranus are quite similar. Uranus is a little bit larger than Neptune, but again, there's mainly gaseous hydrogen and an icy core. Uh, the moons around Uranus were actually discovered with a telescope before Voyager made it out there, and this was actually a picture of of uh, Uranus that it shows the ring. Neptune shows the great storm, and we'll talk about more about that. But looking at Uranus, you can see that it's on its side. The rings go around it. And what's really amazing about this is the fact that the moons that orbit Uranus are on the same plane as the rings. So the moons are actually sideways with the planet. So that's a pretty weird thing. Um, so this planet is sideways, and there's been a lot of conjecture on how it did that. When Voyager went out to Uranus, it found that first of all, it didn't even know it had a magnetic field. But when it measured the magnetic field, they found that the magnetic field was not consistent. It was lopsided, just like the planet. So the magnetic field is lopsided. The dipole that forms that field is lopsided within the planet, and it's out of sync with the axis of rotation. So something definitely hit this planet fairly early in its life. If you compare it to the magnetic field of the Earth, you can see that the Earth is nice and straight and very, very consistent. The magnetic field of Uranus is really cattywampus, and it just doesn't make any sense at all. So it's felt that something kind of grazed off this planet and actually turned it on its side. Bang. So here's the view of Uranus. You can see the banding from the different uh, bands from the Coriolis effect of its very fast spin. It spins once every 17 hours, and you can see it has a variety of rings around it, along with the moons. So again, whatever hit it, it actually turned everything on its side. In 1999, a 6,000-mile wide storm swept across Uranus's surface. The clouds turned out to be brighter than any in our solar system. As you can see here, years later, the clouds that surround Uranus are still bright. And this storm slowly slowly dissolved um, over time. What's even stranger is the fact that its magnetic field actually flips every day. So once a day, the solar wind is able to hit the planet. The next day, it can't. So there is something going on within that planet. Again, probably the lopsided magnetic field that causes that planet to, the magnetic field to allow and then unallow the solar wind to be able to hit it. And finally, we find that the storms that are on Uranus will take weeks for it to develop, and then they might last a year or two and finally dissolve away. The rings are extremely thin, and no one even thought that the rings around Uranus would even be there. Miranda on the bottom was seen for the first time by Voyager. In addition, Voyager found 10 new moons, bringing the total to 15 at the time. So another moon that they discovered going around Uranus was Titania. This is Titania from about 350,000 miles. You can see that Miranda has a very complex surface. And then we have uh, Ariel from about 80,000 miles. You can see these moons are pretty well cratered. And so they were probably hit by asteroids that were coming in from the Kuiper belt. If you compare Uranus and Neptune, you can see that, again, Uranus is on its side. The B part of Uranus, you can see we have the bands. We have a very high contrast picture of them showing the different bands going around the planet. On the bottom, we have Neptune. Neptune rotates about the same as Uranus. And you can see that the E is actually a picture from the Hubble Space Telescope, and it has some very bright clouds and some very active storms on the surface. Like Uranus, Neptune does not have a solid surface. So let's go ahead now that we're done with Uranus. Still many questions with that. We just don't have time. Neptune is the next planet out, and immediately you can see the great dark spot on the planet. This is an Earth-sized storm. And like Uranus, there is no solid surface. And given time, we find that the storm will actually change shape. And the big question is, where does the energy that powers these storms, where the Neptune receives only about 3% of the energy that Jupiter receives. So Neptune actually gives off more than twice the energy that it gets from the sun. Of course, Saturn and Jupiter also give off more energy than it gets from the sun. Uranus is the oddball here. The fact of the matter is that Uranus is actually relatively cool compared to these planets. Anyway, but we find that the winds around that great dark spot move at about 1,500 miles an hour. The storm was a very big surprise. Uh, and then and the fact that it covers so much of the planet. Uh, they Scientists actually increased the contrast to be able to see the banding and the storm more on this planet. And then when we looked at that great dark spot, we find that over time it does change shape. It discovered large-scale storms. It also discovered the mass of Neptune, 6 of the known moons that orbit Neptune, and the fact that Neptune has rings as well. So the storms on Neptune are quite amazing. But what's amazing also is the fact that in 1994, the spot vanished. It was gone. Neptune did not have any surface features that would indicate a storm. And then less than a half a year later, it was replaced by another storm, this time in the opposite hemisphere. So something was going on with that. They just didn't know exactly what. They think it might have to do with the fact that Neptune may have been a little bit closer to the sun, and therefore some of the climate on, Neptune may have changed a little bit. But Neptune does show multiple storms, and it also shows the fact that it has a great deal of heat. And it's because of this heat and pressure that's on not only Neptune, but also a bit on Uranus as well, that both Uranus and Neptune are able to manufacture diamonds in the atmosphere where they could be falling like rain toward whatever surface or whatever hard ground there might be within the planet. Maybe it's a whole layer of diamonds. That'd be an interesting thing to pick up. Anyway, but how do diamonds form on planets like this? Well, first of all, you have to have a methane-rich atmosphere. And then you have to have, during storms, you have lightning, which will turn the methane into soot. Heat will change the soot into graphite. Graphite with heat and pressure will become more solid, and these chunks of graphite undergoing pressure and heat will be compressed and will actually form diamonds, which is really kind of hard to live with. Oh well. So Neptune might be a good place to visit if you want to get some diamonds. But on the way there, you would also find that it does have a ring around it. Not as prominent as Uranus, but definitely a ring. Looking at some of Neptune's moons, like Triton. Uh, Here's Triton, and as you can see, Triton has a very interesting surface. You have a smooth surface and a rough surface. And it seems to be right at a point where this particular moon seems to be undergoing change. The proximity of this particular moon to its planet is such that the tidal forces of gravity actually cause the surface of this moon to flex. As a result, there are ice volcanoes on the lower side of this particular moon, and they are spewing ice. It is part of the problem is the fact that it's rotating backwards. And as it does that, it's in, well, it's in conflict with the planet itself. At some time in the future, it'll get to the point where it'll fall toward the planet close enough for the tidal forces to rip this moon apart and actually become a ring around this planet. But don't look for it anytime soon. They're predicting that in about 100 million years. What is startling about this is the amazing lack of craters that's on the surface. The fact that the surface is changing. It absorbs those craters and the smoothness basically prevails. But on part of that moon, there are rough areas, and there are lots and lots of cryovolcanoes. Two other moons were discovered by Voyager. They have some nice names to them. I'm sure they're renamed by now. And again, looking at Neptune by using the Hubble Space Telescope, they are seeing more and more storms developing on that planet. If we take a look at the magnetic field of Neptune, we find that it's more cattywampus than Uranus is. The dipole for Neptune is very much off center. And as a result of that, it gives the impression that Neptune was hit by something as well. So right now, the most modern theories concerning both Uranus and Neptune was the fact that Uranus had an oblique impact, which caused the tilt in the rotation, and Neptune had more of a head-on impact, which led to the fact that the interior of Neptune is somewhat, wow, it's definitely somewhat mixed up. So now that Voyager has passed Neptune, that it actually passed Neptune in about 1990. Here it is, basically 30 years later, and we find that Voyager has left the influence of the sun's atmosphere. We have galactic cosmic rays have increased. The heliospheric particles, in other words, particles from the sun, have dropped off tremendously. At that point, the Voyager 2 has left the heliosphere of our sun and is now traveling in interstellar medium. And it is well on its way toward the beginning of our Oort cloud. It should reach the very beginning of our Oort cloud in about 300 years. It'll reach the outer edge of our Oort cloud in about 30,000 years. And once our Voyager probes leave the solar system entirely, they will orbit our Milky Way galaxy along with everything else. And in a little bit less than 300,000 years, it'll pass within about 4 light years of the star Sirius. Now you may wonder, I mean, so we're sending this thing out there. Is there a way that, what happens if somebody should happen to pick it up? Would they know where it came from? Because even from Neptune, our Earth looks like that. So there wouldn't be any way that they would be able to know that that little point, that little spot was what sent that probe out. So they decided to put a luggage tag on it. And they put a luggage tag that looks like this. It's a record. And on one side of the record, it gives instructions on how to play it. And the groove side of the record is where they drop the needle and they can listen or gather data about Earth. Sitting on that record is a little bit of uranium-238, which is electroplated onto the record. Uranium-238 has a half-life of 4.5 billion years, which means that it's hoped that the intelligent community that happens to find this apparatus would be able to estimate how long this particular probe was in space. Now, you're probably wondering, what do all those marks mean on that right record? Well, here's the translation. And as you can see, it gives a fairly scientific view of what's on those diagrams. What I don't quite understand is if they're going to build a phonograph in order to play that, will they even be able to, it's assumed that they'll be able to figure out what's going on that record. Do you think they'll be able to figure that out? Do you think that when they hear voices or data coming off that record, they'd be able to tell what's going on? I sure hope so. It would be an interesting test to see if there really is intelligent life out there. Okay, next week, we are kicking off a 100-year celebration. Actually, the celebration won't last 100 years, but actually in about 11 days, we are celebrating the 100th anniversary of the placement of the cornerstone for the Drake Municipal Observatory. The cornerstone is actually the mosaic that's on the floor inside the rotunda, because that gives a date as to when they started construction. And the party, the year-long party, will start in January of 2021 and will culminate in November of 2021 at the anniversary of the opening of the observatory. So I hope you'll keep us in mind. And next week, we're going to be talking about the observatory. So I hope you'll join us for that. And we'll learn more about how Drake Observatory was built.